progressed within this IPCC assessment to produce information that is much more useful. So in that sense, I'm going to be talking about how do we assess regional changes. We're going to be introducing this term climatic impact drivers. So how do we assess regional changes in climatic impact drivers so that we can inform regional adaptation and risk management? And in that sense, the goal of this chapter that I'm going to describe is to produce actionable climate information in support of those making decisions. So as Clara mentioned, I was the coordinating lead author for Working Group 1, Chapter 12. And just to get it out of the way, the formal title of that chapter was Climate Change Information for Regional Impact and for Risk Assessment. All right, so just as some quick background, the IPCC 6th assessment is an update of the last assessment, the 5th assessment report, which came out in 2013 and 2014. The full IPCC 6th assessment cycle includes 3 special reports. There's a special report on global warming at 1.5 degrees, special report on oceans and cryosphere, and there's a special report on climate change and land. In addition, there are the 3 traditional working groups. Working Group 1, which focuses on physical climate science. Working Group 2, looking at vulnerability, impacts, and adaptation. And Working Group 3, which focuses on options for mitigation in the context of development and other socioeconomic changes. That full set of special reports and working groups reports culminate in a single synthesis report, which is the summary of all of the 6th assessment cycle. I'm also involved in the synthesis report, so we're going to be continuing to work on this for a little bit longer. We began working on Working Group 1 back in 2018 and released the Working Group 1 report on August 9th, 2021, so about a month ago. Working Group 2 is expected in February, and Working Group 3 is expected in March, with the final synthesis report coming around this time next year. And those who know the UN Framework Convention on Climate Change might know that there is a Conference of Parties, a COP meeting, scheduled for November, which now falls between these working groups. So one of the things that people are trying to figure out is how will that climate information feed into the negotiations at that Conference of Parties, considering that there are huge reports just around the corner that will provide important context. Those who don't know the IPCC assessment process, it is a massive effort with hundreds of scientists all around the world, commissioned by the UN Framework Convention on Climate Change, and therefore subject to a lot of the UN type policies. And in the end, every word of the summary for policymakers is approved by all of the UNFCCC countries. So pretty much every country in the world approves every word of the summary for policymakers and goes through all the figures and numbers with a fine-tooth comb. That process, the summary for policymakers is, on the order of 40 pages or so when you count in a bunch of figures and things. That is just the summary of what in the end is about 4,000 words. Now I'm getting myself confused. It's about a 4,000 page set of reports that you get in this Working Group 1. So there's a lot of material that is boiled down into this summary for policymakers. The information and the emphasis in this set of results, this new assessment, is an emphasis on regional climate changes and actionable climate information. And you'll see a lot of attention paid to the detection and attribution of extreme events and climate trends, which is one of the many new fields that has substantially evolved and progressed since the last assessments. So there's a lot of material in here, but this just gives the context of where this IPCC assessment is coming from. Our own chapter was written by many of the people you see on the screen. Just to make it fun, this is the author team mixed in with a minstrel group at a place where we went out to dinner. So see if you can figure out who are scientists and who are medieval minstrels. Sometimes it's harder than you might think. But the Chapter 12 team was really fantastic. We had people from all around the world, colleagues from United Arab Emirates, from China, from France, Italy, Portugal, Bangladesh, Iran, a bunch of really interesting, diverse, great scientists. who came together to make this chapter work. So the overall idea of Chapter 12, again, the title is Climate Change Information for Regional Impact and for Risk Assessment. And I would argue that the surprisingly important word in our title is the word for. We are not actually doing regional impacts or risk assessments. We are producing the climate change information in support of those things. The first thing we had to do as part of this process was develop and connect to a broader risk framework. I was part of a publication that came out in late 2020, which is a new guidance document on the concept of risk and how it is handled in the IPCC Sixth Assessment Report. Maybe just as a shorthand version of this, it's important to recognize that risk is an intersection of hazards, vulnerability to those hazards, exposure to those hazards, and potentially the responses to other changes in terms of how risk can be affected by not only the hazards, but the responses that we take. So when you put all those things together, Working Group 1 really is the place where we focus on hazards. We're trying to figure out what types of climate change are important, and then Working Groups 2 and 3 figure out kind of where are we vulnerable, how are we exposed, and how would we respond. It's a challenge actually to draw these working group lines because they're somewhat artificial. In the end, people who are working on risk are putting all these things together, but the reports are supposed to be just the physical science, and then later comes the vulnerability, etc. So one of the things that we set out to do in our Working Group 1 efforts was to define the types of climate changes that affect society and ecosystems. So this is where we developed this climatic impact drivers term to produce climate change information that feeds into this risk framework. And I'll go into this more in the next slide. The goal then is to take this set of climate changes that matter and connect them to those specific sectoral responses across the various parts of nature and society that we are interested in. This helps us focus information not just on standard climate variables, but on the specific response thresholds and metrics that we need. Then we would assess each CID and assess the changes in each CID for all regions of the world, and then compare these changes in CIDs against global warming levels. I'll go into this more in a moment, but it's important to understand the fundamental response to the global signal of each of these types of climate change. And then, of course, we want to connect climate information to the climate services. So when you put all of this together, what we're doing is we're defining the types of climate information that matter, connecting them to the sectors, looking at them on a region by region basis, and then scaling up to kind of global connections. So the climatic impact driver term is important to just put on the table here, and it's 2 sentences long, and both are quite important. Climatic impact drivers are physical climate system conditions, for example, means, events, or extremes, that affect an element of society or ecosystems. Depending on system tolerances, CIDs and their changes can be detrimental, beneficial, neutral, or a mixture of each across interacting system elements and regions. So it might be helpful here to break this down into 2 terms. The noun here is impact driver. And it's important to note that there are many types of impact driver that could lead to some kind of impact on a system. There are, for example, earthquakes or socioeconomic development can cause an impact. Geopolitical conflicts or even something like COVID-19 we've all seen can have a big impact. But of course, IPCC is concerned with the climatic impact drivers, those things that come from the climate system that drive impacts. And one of the main purposes of the CID framework is to ensure that the physical climate information is not overly generalized to be universally detrimental or beneficial, because we recognize that there are substantial differences across regions and across sectors, and even the system elements within each sector could have slightly different responses. So rather than us as climate scientists saying that a particular thing like wildfire is always a hazard, of course, you can come up with examples of forest systems that require a fire cycle, or other examples like this that show that there are potential benefits, and we can't be so universal in how we speak as climate scientists. So in the end, we created this inventory of climatic impact drivers of relevant types of climate information. There are broad categories here. Heat and cold are largely connected to temperature, wet and dry for precip, and as you can imagine, wind, snow and ice, coastal, oceanic, and other categories form the kind of first approach at this. But then within these, you see specific categories, specific climatic impact driver types, such as mean air temperature, which is the average conditions, includes also things like the seasonal cycle, extreme heat, which is more than just temperature, but can factor in things like humidity that interact with heat conditions in terms of the way that sectors respond. There's also cold spells and frosts. And then as you go across this list, I won't read them all out, but you see that these are broader categories, each of which can be further elaborated with specific indices and metrics, which we describe in the chapter. And that as we're looking at the way these different types of climate, these different climatic impact drivers, these different types of climate changes that we care about, we want to understand how they change in their intensity, but sometimes it's more important to understand changes in frequency or the duration of an extreme event when it does strike, or the timing of that seasonal event, for example, in different phases, different parts of the growing season, and then also the spatial extent of where these things are potentially happening. For example, tropical cyclones moving in terms of the latitudinal bands in which they are dangerous. So all of this is the types of information that we need to understand. And within this chapter, we first define all of these, and then we map each of the sectors to basically ask which sectors require which types of climate information based on literature in terms of what climate information is used for impacts and risk assessments. So you can see here where we have dark colors are places that are strongly connected. For example, crop systems are dependent on the seasonal temperatures, but can have a very strong response to extreme heat. They also can have strong responses to frost and cold spells. But as you can imagine, things in the precipitation category are quite important for agriculture. And then you can go further down this list and find things like hail, which can be devastating when they hit a crop field, for example. And here we've just shown a couple of these to emphasize that the pattern or the types of climate information you might need for crops are slightly different than the types of climate information you might need for livestock and pasture systems, and even more so different from what you might find if you care about fisheries and aquaculture as part of your overall food system. As you can imagine, the coastal and oceanic things matter more. So we've mapped this out. This is just a portion of a much longer table with these broader sectoral categories. And in some places, we even distinguished the loss of a season's crop from the loss of agricultural land as a resource, where you start to have things like relative sea level mattering more. Here's just an example of some of the indices that we look at here. This is the NOAA heat index, which has a threshold when the heat index exceeds 41 degrees Celsius. NOAA declares that to be dangerous conditions. And what you're looking at here is a projection across the CIMIP 6 climate models, looking at a couple or several different scenarios and time periods, but looking at the change in the number of days where we exceed this heat index. And as you can imagine, the heat index is increasingly exceeded in tropical areas, but even in parts of the United States, we are seeing weeks, if not months, of these dangerous heat conditions every year. And this type of dangerous heat condition is associated with impacts on livestock, with outdoor laborers, including farm workers and construction workers, and also things like the ability to have the U.S. Open or a golf tournament or a marathon and other recreational activities. So each of these things are mapped out and connected, so that when we're producing information, it's not just temperature changes, but this type of more useful index, which can feed into the impacts and risk assessments. One other thing that we did, because it was very difficult to always come up with a single threshold, we started to identify patterns and look at how different sectors respond to increasing temperatures, for example, in this plot. So one way to think about this is the kind of average conditions are located in the middle here. And as conditions become hotter, you move up. And as conditions become colder, you move down here. And different sectors have different thresholds that are commonly looked at. And they are important even as they may differ from one group to the next. The same types of thresholds appear over and over again. So many of you know I spend a lot of my time thinking about agriculture, so I'm always drawn to the agricultural column here. But just as an example, there is an optimum temperature by which most cropping systems are designed. And as it gets warmer, you start to move up towards what we would call a critical temperature. And that critical temperature starts to have reductions in crop yields. When you get hot enough, you start to run into different types of pests or limitations for pests. And then if you go far enough, you can get to a condition where the crop actually fails. So the specific levels, as you can imagine, for this critical temperature or this limiting temperature are very much dependent on the crop species and the farm management and the seeds that you have chosen. So rather than us trying to specifically assess every single threshold, we rely on the fact that there are patterns and encourage those seeking climate information to focus on thresholds if they can be identified. The next thing we do within our chapter is we take this full list of climatic impact drivers and we assess their changes across 51 global regions of the world. Here we've just looked at the North America regions. Many of you might first look at this and say, you know, these are very broad regions. We had the same response. You might notice that Miami is in the same region as Detroit or Nova Scotia or New York City. So these are broad regions, but again, meant to be the first kind of assessment. And these regions were designed by the IPCC Atlas to represent broadly similar climatic types, even as, again, those specific thresholds might be more regional. And in that sense, what we're doing here is encouraging beginning of a deeper climate information assessment. But their broad categories and the broad regions can still provide a lot of useful information. So here where you see red, we have a high confidence that this CID is increasing. So for example, in all North American regions, we have high confidence that the mean air temperature is increasing. We also have high confidence that extreme heat is increasing, but cold spells and frosts are decreasing. That's why we see blue here. And you can go across different climatic impact drivers and notice that we have less confidence in certain types of climatic impact drivers. So in general, the drought categories here, where we have hydrological drought representing surface water and agricultural and ecological drought largely representing soil moisture and available kind of root zone water. These tend to have lower confidence no matter where we look in the world, and often have these footnotes in the table because they have additional kind of sub-regional information that's worth noting. For example, stronger summer effects than winter effects, or some kind of within region pattern that we wanted to note. You'll also see that there's very strong confidence for something like a lot of the coastal and oceanic changes like sea level changes and marine heat waves, and of course the overall ocean acidification. The final thing you'll find in these tables are these dots, which represent the emergence of the regional signal. When we see black here, we're saying that the regional signal has already emerged and can be attributed, but where you see purple dots or light dots, we are assessing that those changes will emerge in the mid or late century under a higher emission scenario. You'll also see some things like hail here, which have low confidence in the direction of change for all regions. This is a combination of the physical understanding, the observational data, and the literature just not having enough to support a confident assessment. But this is something that we have used as a kind of approach here, that when we can align those multiple sets of evidence, when we see an observed trend that can be explained by physical understanding, can be connected to the human influence, and matches the kind of direction of the projections, we have very strong evidence to produce these confident assessments. Okay. So when you put this all together across the various tables and assessments within Chapter 12, we hope that readers can find themselves in this report. So here we've just taken some pictures of different systems in different parts of the world. So here in Victoria, Australia, this is meant to represent people who are concerned about coastal erosion. In Dhaka, Bangladesh, those concerned about cities and livelihoods in a low-lying delta. Cape Coast, Ghana, this is the fishing fleet of a small village in Ghana. We have agriculture in France, we have rainforests in Brazil, and flooding in the kind of outskirts of Delhi in India. People who are concerned about this should be able to find the information relevant to their sector of interest and a general assessment of the regional changes in the region that they are concerned about. So this should be enough to at least initialize and provide a good starting point for the continuing climate information and climate impact and risk assessments that will be further bolstered by what comes out of Working Group 2 and Working Group 3. Maybe just a couple other big messages that come out from the top of all of this are that every region of the world has more than one type of climate change, more than one climatic impact driver changing with high confidence. This suggests that the future cannot be approached with a one-at-a-time approach to climate adaptation or mitigation challenges, but recognizing that there are multiple overlapping challenges in all regions. And here what you're seeing are icons just representing where we have high confidence. And if we go to the medium confidence, there's even more to begin to prepare for. Maybe just one other thing I wanted to show here is a little bit of how we've handled uncertainty. This is a map looking at an index of the number of days per year where the snow water equivalence is at least 100 millimeters, which is a threshold that's been used to denote the potential for recreational skiing, whether it's cross-country skiing or downhill. And you can see in most of the continent, we have this dramatic reduction in the number of days per year where we have these types of snow conditions by this mid-century RCP 8.5, so a high emissions scenario. We also break this down by different global warming levels, by different time periods, and by different types of model collections. So for example, the CIMIP 6, CIMIP 5, and CORDEX. And then of course, within those, we have a breakdown of the model uncertainty in terms of the way we look at this box and whisker. So this type of information helps also kind of give an idea of how confident we are in different regional changes. And again, hopefully provides the reader with a starting point to pursue further model information. Now, I do want to say just one word about this idea of comparing against global warming levels. First of all, it's very interesting, at least to me, that this IPCC assessment has pushed so strongly for global warming levels as a fundamental kind of way that we present climate information. And just to be clear, what I'm talking about here is looking at the global temperature, the global surface air temperature as a kind of measurement of the overall climate change signal. And then asking the question whether the more specific regional changes or even changes in extremes follow some kind of linear response pattern or are strongly connected to that global warming level itself. So here in the upper right, you'll see an example. This is North America, and we're looking at the hottest days of the year and how do they change in comparison to the global warming levels. And what you see is that basically as the global warming levels go up, the extreme temperatures go up even faster, such that, you know, a global warming level of 2 leads to extreme temperatures going up by more like 3 or 4 degrees. That is a pattern that also allows us to cast each of the scenarios on top of each other and basically allows us to compare the high emissions and the low emission scenarios, because the fundamental physical finding is that when the global warming level is reached, the extremes respond quite linearly and rapidly to that global warming level, such that we get a similar reaction whether that global warming level was achieved under a high emission scenario in the next decade or under a low emission scenario farther down into the future. So this is true, and this linear response was assessed with high confidence for a large set of the CIDs, but not all of them. Oceans and cryosphere tend to have a much slower response to this global warming level, and that leads to nonlinearities and uncertainties in terms of how different regional responses respond to the overall global signal. In general, what's often found is that if you give enough time for equilibrium to be reached, a lot of those responses are also quite linearly connected to global warming levels, but that lagged response really does complicate things. And of course, if you are actually producing a plan for a new adaptation investment or a new mitigation or planning risk management, time does matter, because we need to know how much time we have before that new set of climate conditions comes in. So I would encourage, if you haven't looked at this yet, check out the way that IPCC is looking at global warming levels as a fundamental way of organizing the climate information. One of the maybe side benefits of this is that it has allowed the physical climate scientists to avoid getting caught up in the conversations about which emission scenarios are most probable or likely or practical. These things, of course, will be dealt with within Working Group 2 and Working Group 3. But the basic idea is that climate information is quite strong in showing that the response of even regional extremes is quite well connected to the overall global warming levels and therefore the emissions that underlie. Okay, so now I'm going to get to some of the broader IPCC assessment findings that are worth sharing in this forum here. As you can imagine, with about 4,000 pages and many chapters that I haven't focused on, there's a lot of information here, and people at GISS are studying every part of the climate system. So I apologize if I'm not focusing on your specific element, but I did want to call out a couple of these things that are specifically connected to this regional climate impact challenge. First is that it is indisputable that human activities are causing climate change, making extreme climate events, including heat waves, heavy rainfall, and droughts more frequent and severe. This is a step forward from the previous IPCC assessments, which largely had broad messages based around global temperatures and climate change being connected to humans. But now we're really getting to these extreme events and the regional events, and saying that we have strong evidence that these are connected to human activities. So this is kind of where that comes from. This is a kind of novel hexagonal representation of world regions. And if you squint your eyes and look at this, eventually you can start to make out continents like North America, South America, Africa, Eurasia, and Australasia, and some small islands here. But the basic idea here is to focus not so much on the geography of these regions as much as the common kind of signals that we're seeing. So here we're looking at changes in hot extremes and finding that we have attribution studies showing the human influence on nearly every part of the world when it comes to extreme heat. When it comes to heavy precipitation, all of the green hexagons here are places where we have attributed heavy precipitation increases to climate change. And in the oranges here are places where drought has been shown to have been increased by climate change, and even some places where decreases have been attributed to human influences. So when you put this all together, it backs up this statement that climate change is already affecting every inhabited region across the globe. And we can really see the human influence on these climate extremes. The other big message is, sorry, I have something on my screen blocking it. Here we go. The other big message is that climate change is already affecting every region on multiple ways, but further, that changes that we experience will increase with further warming. And the language that we use specifically says that these changes in climatic impact drivers will be more widespread and more pronounced with every increment of climate change. So this basically says that the patterns that we're seeing and the patterns that we're projecting are going to extend. They're going to become more pronounced as the climate change increases, which again focuses our kind of information on the idea of establishing these patterns, because then basically the extent to which they move is going to be based on how much we emit. So this actually ends up being an empowering message, because what it says is that if we want to slow down this pattern of change, if we want to halt or even reverse this pattern of change, we have the ability to do that if we can get emissions under control, if we can stabilize the climate system. So think of this. I think that the piece of optimism I get from this is recognizing that human ability that we can make a difference in terms of what that future will look like. Let's see. All right, here's just a couple more examples of the IPCC projections and how we've presented some of these changes. This is a representation of heavy precipitation and how it will change, and we're looking specifically at the 10-year event as it's been experienced in the past. So the 1 in 10-year event, of course, in the past used to happen only once out of every 10 years, but that same amount of precipitation as the climate changes is going to reach up to 2.7 times every 10 years under this 4-degree world. So that's, a 270% or I guess 170% increase in terms of how many events we would get in every 10-year period. Another way of doing this is you kind of flip it around and you ask, what will be the new 1 in 10-year storm if we get to a 4-degree world? And in that sense, that new 1 in 10-year storm will be 30% wetter. So this gives us an idea of what we consider extreme now will happen more often, and what will in the future be considered the kind of same level of statistical extreme is going to be that much more severe. The other thing that I wanted to highlight here is that there's a new effort within this IPCC Working Group 1 report to not stop at the year 2100, but to actually look at the fact that climate changes have effects that extend well beyond the end of this century. And here we're looking at global mean sea level changes extending not just from recent past to present and out to the end of the century, but all the way out to the year 2300. And it's really important to note that even those high mitigation scenarios, this SSP 1 2.6, which is a strong mitigation with net neutral carbon emissions and even negative carbon fluxes by the end of the century, even that scenario has dramatic sea level rises by the time you get out to the year 2300. Whereas the higher emission scenarios, this SSP 585, where you're basically burning all of the coal and oil and other resources, fossil resources that we have, that even on its lower end is quite substantial. And the upper end actually extends off of what this chart would look like all the way up to 15 meters. That can't be ruled out. This is the one of the last slides I'll show here, which is coming back to these climatic impact drivers. When we look across all of these climatic impact drivers, and we look across all of the regions that we've assessed, we can ask some broader questions. For example, in all of the regions where the mean surface temperature could be increasing, it is increasing in terms of our projections. In nearly all of the regions do we see in high confidence of extreme heat, with just a few where we have medium confidence. But when we get to something like cold spells, pretty much all of the regions are decreasing. And this basically is another way of us saying that there are certain types of climatic impact drivers that are effectively changing over the whole world with confidence. Whereas there are other ones like aridity, where you see some regions increasing in aridity, getting generally drier, and other regions where aridity is decreasing, they're getting generally wetter, but also lots of regions where we don't have confidence. There are other things like tropical cyclones, where if you look at the regions that are currently susceptible to tropical cyclones, it's only a subset of all of the global land regions, which is why this shading kind of scoops in here. But in pretty much all of the regions where tropical cyclones have an effect today, we are seeing medium confidence of increases. And there, if you follow the text, what you see is that increase is based more on intensity and the amount of precipitation associated with those tropical cyclones rather than an increase in frequency. So that's an example of how kind of figuring out exactly what type of increase of your CID really matters. There are other things like hail, which I mentioned earlier, where we just don't really have strong information anywhere in the world. So this becomes a research challenge and very difficult to plan for. Likewise, something like atmospheric CO2 we know is going up everywhere. Ocean acidity, marine heat wave, and a lot of these coastal things are pretty much universal wherever they could be affecting. Okay, the last thing to mention here is that there is also now an IPCC interactive atlas. In the past, the IPCC atlas was a static publication of maps, but now the atlas is effectively another chapter within IPCC, and they have produced this digital version where you can actually go in and query different data sets, variables, time periods, scenarios, and even seasons, and get a whole number of really interesting maps quite rapidly. There are also information from regional models, different generations of the climate models, and there is also a way now to look at the map of CID changes for any of the CIDs, and even to build interesting combinations. For example, can we find places where drought is increasing and where heavy precipitation is increasing? And the answer is yes, there are several places where we are seeing both extremes of the water cycle intensify. Okay, so to summarize here, the IPCC sixth assessment report is out, at least working group 1. There are lots of associated resources well beyond what I could present today. Within our chapter, we are really proud of the Climatic Impact-Driver framework, which has been adopted across all of working group 1 and the other working groups as well to make climate information more actionable. This is also in direct response to what the UNFCCC negotiators requested for more actionable information. Within our chapter 12, we delineate CIDs from climate variables, connect these to the sectors, assess CID changes for each region, and then look at how CIDs respond to the global warming levels. And as you can imagine, there are lots and lots of specific combinations when we do all of those things. And I appreciate your attention and would be happy to discuss more. Thank you so much.
Great. Thanks so much, Alex. That was a really nice summary. So let's see. Does anyone have any questions that they would like to ask? If so, please just indicate in the chat. So I guess as we're waiting for people to write some questions, I guess I have a question about so internal variability in all these different metrics, especially some of these more compound metrics that depend on kind of dynamical fields like wind speeds, for which I think one of your charts did indeed indicate kind of a low confidence. Did you find there was a lot of discussion about kind of, revisiting ensemble sizes that we use to detecting forced signals versus internal variability? Is that kind of a big part of the discussion here? Or is your impression that kind of the uncertainties associated with other factors are just overwhelming that part of the story?
So, we would have a longer conversation for any one of the CIDs in terms of how we actually, went about doing that. And it's also important to note that some of the CIDs, even though we assess them in a broad region like Eastern North America, of course, the analysis is often done on a much finer basis within that region, and then kind of we aggregate the message that comes out of that. But yeah, on something like winds, we have there were some studies that really did look at the ensemble of models and looked at kind of separating that longer term signal from the internal variability. That would be one reason why you would have medium confidence rather than high confidence when you find strong model disagreement. When you find that the kind of signal to noise ratios are quite small, that's the kind of thing that would make us reduce. But we kind of also separated it a little bit in terms of the way we talked about emergence was largely that signal to noise issue. The way we talked about confidence was largely around this this multiple lines of evidence approach, where we said, if we have that physical understanding with models that seem to agree, even ideally, when we ask tougher questions like, what if we had just the final resolution models or the downscaled versions, that gets us to the confidence levels. Now, one other thing that you touched on, which maybe I'll leap off of, is this idea of compound events, or what I would call maybe more broadly connected extremes, which could be more than one thing happening at the same place at the same time, like a river flood the same day you have a nor'easter, with coastal flooding, or it could also be when multiple regions are hit by extreme events at the same time, like a multi-breadbasket failure. And then finally, another connected extreme would be sequential events, where the effect of a fire leads to a higher possibility of mudslides, things like that. So we did look at that, but as you can imagine, the science gets more and more muddled as you start to add in conditions on top of conditions, right? And there is some effort, of course, to look at teleconnections and other things that would cause these things to be correlated beyond just the chance of two events happening at the same time or in sequence. And that is something that we actually were able to make stronger statements about compound events increasing with climate change. And part of it also is just that some of these background things are happening pretty much everywhere you look, like extreme temperature increases. So pretty much everywhere you get drought, it becomes, a hot drought. And everywhere you have, a heavy precipitation event, you have to worry about how it would overlap with coastal flooding.
I guess just because you were talking about confidence, did you also think that, in addition to internal variability, there is just, okay, so I do see that there's one hand raised, but there's just the issue of certain models performing historically better than others. Is there any kind of explicit consideration of that when you do weigh one model relative to the other, or are they all kind of treated the same? I don't know how that's factored in.
Yeah, I mean, so the weighting, if you're talking about like kind of the weighting of ensembles
Yeah.
and things like that, that was done. So one of the things our chapter did is we summarized assessments across lots of other chapters as well. So there was a lot of talk of weighting, especially when it came to the equilibrium, climate sensitivities, and things like that, in terms of how you would weigh that. But mostly what we were doing is we were basing it on the literature. So I can't say there was only one approach there. It was more that we would kind of look across the literature. But in general, this is kind of part of the task of being the IPCC folks, right? Is you have to decide whether a weighting criteria is critical to a literature kind of being part of the assessment, right? If it was done properly, or how do you factor that into your uncertainty? So I can't give you a single answer here, other than to say that whenever we were looking at models, we would ask whether the model was credible, if there had been kind of efforts taken to justify inclusion or exclusion of different models. And we did kind of, by associating by different types of things, for example, the average wind speed, we're able to kind of hopefully circle in and get the more precise climate information that's needed.
Okay, great. Okay, so we have a comment here from Ron, and then I also see that Olivia has her hand raised. But first, I'm going to just repeat Ron's question. Ron says, "Great talk and great work. Some of these CIDs, like dust storms, depend upon highly uncertain changes in source extent that was not even varied in some of the models." So he says, I don't think that the SSPs prescribe the dust source area. So how did you deal with this uncertain future inputs when estimating drivers such as these?
Yeah, so that would be a good example, dust storms, of something where we did not rely too much on the global models. The global models often are producing the kind of larger scale aridity patterns and maybe some of the general circulation patterns. But the actual studies that we look at for dust storms are largely based on kind of regional models and other assessments like that try to explicitly look at this. So that the literature around something like dust storms tends to come from kind of subsets of models and other groups that have specifically set out to do dust storms, rather than just drawing it out of what you get from the global models. We also base that oftentimes the observed trends give us a lot to work with. And a lot of times the people who are planning for dust storm activities use proxies like larger scale aridity as a major kind of emphasis. Another one, for example, I know we have a GISS extremes workshop coming up. But when we're looking at severe windstorms, things like thunderstorms and tornadoes, you wouldn't expect a global model to do that well. So we look to regional models, and we also look to proxies like the stability of the atmosphere, or CAPE, convective available potential energy, and other things like that. So one of the things we do in this chapter is we lay that out. We say, when people are assessing this, this is the type of climate information they often use. But you won't see too much high confidence information around things like dust storms. I'm checking here, in terms of what you'd find. So yeah, sand and dust storms, you can see is not many regions have much to say on that.
Great. And so I can see that Olivia has raised her hand, so I'm going to unmute her.
Okay. Hi, Alex. Thanks for the great talk. I realized that you're not an atmospheric chemist, but I'm wondering whether you can comment on the air pollution meteorology term. I assume that means that you're looking at changes in air pollution that just occur with meteorology and not anthropogenic precursor emission changes. And so and if so, I guess I'm wondering, why you chose to look at that metric, especially given that they're, assuming reductions in carbon dioxide, it's reasonable to expect that there could be reductions in anthropogenic pollution precursor emissions as well.
Yeah, thanks, Olivia. It's a great question, and I applaud you for zooming in on one of the hardest ones. Yeah, because that was a really tricky one that we were discussing right up until the very end. So there are two of our CIDs that are specifically defined with weather there. So you see fire weather and you see air pollution weather. And on both of those, the reason we did that was to very strongly draw a line between the meteorological conditions and the human conditions that are beyond the specific purview of Working Group 1. So you can imagine fire area depends a lot on how we fight fires, how we manage forests, and a bunch of things like that. But fire weather is something that we can model in our simulations. Similarly, for air pollution weather, we were looking at things like blocking patterns, stability, that would cap Los Angeles or a place like that and lead to smog conditions. We were looking at the temperature effects that could lead to kind of ozone production and particulate matter transport and things like that. And in the end, the air pollution, the air short-lived forcers chapter really were not comfortable with us on a regional level making too many strong statements. This is an area where, as you said, us not being, me not being an atmospheric chemist, we strongly deferred to them on this. And they do have discussions. So, we talk about air pollution, whether the indices, the importance, how people go about doing it. But in the end, we kind of back off and say that the kind of on a regional basis, we don't have enough confidence, and especially not enough confidence when you factor in that the signal of the meteorological feedback or the meteorological augmentation of the much larger emissions question is really what would we would be kind of emphasizing there. So the emissions question when it comes to air quality is so much bigger than the kind of additional factors of the local meteorology. Or at least our ability to see human influence on those changes in the local meteorology, that it was very difficult for us to make strong statements. So we do say, future air quality depends strongly on emissions and air quality policies. But, of these air pollution meteorology phenomena, we don't have enough to make a confident statement on a regional basis, at least.
Cool. Thanks for going into it.
Mm-hmm.
Great. So any more questions? Can't see any more raised hands, and I can't see any more in the chat. So last call. So I think with that, I want to thank you again, Alex, for giving a great summary of this chapter in the report. And I just want to remind everyone that this was recorded and we are going to post it. It should be up within about a week or two. So with that, I want to thank you and thank everyone for coming, and have a great day.
Thanks all.
Thanks, everyone.
Thanks, Alex.
Bye.